Hello students, welcome to class 26. Today we'll go for the another concept of this organometallic catalysis, that is polymerization and isomerization. Okay, so these two concepts are there. So we will see whether we could complete these two in one video or we will shift one of the concept in the another video. So what is this polymerization? So uh, it was been best catalyst homogeneous was used is your Ziegler nut catalyst. Okay, so this is what which is going to convert your alkene to polyalkenes, alkenes to polyalkenes. So one of the very important application of the organometallic compounds, and this was developed by German physicist. Okay, this was German chemist, uh, German, yeah, it's not physicist, it's a chemist. He was a chemist. Okay, German chemist in 1953. Okay, and he developed this catalyst on the titanium halides. Okay, titanium halides with organo aluminium compound. Okay, so that is what the two components was been taken for preparation of this. Okay, halides of transition elements was taken. So even today we can see there is titanium along with this iron and other molybdenum and other transition elements of other group elements is been taken from fourth group to seventh group. So you can see that some elements are taken into this in preparation of this Ziegler-Natta catalyst along with the titanium. So this is what, and even with the halides, aluminium, alkyl hydrides of aryl or alkyl metals from the first group to fourth group is taken for the preparation of this what you say this Ziegler-Natta catalyst. Okay, so this is what about the catalyst used here for the polymerization. Now this catalyst, it's having somewhat the compact structure, that is a cubic close packed structure. Okay, with so which is prepared by taking TiCl4 plus AlC2H5 thrice, okay, in the solvent hexane. So you are going to get the what you say you are going to get the catalyst here. So where you can see titanium is in 4 state in this way, CiCl4, and aluminium is in this way, and you can see there is a bond between the chlorine phthalene like this and titanium in this way. Okay, so this is how we can see that chlorine to aluminium like this, sorry, not here. So chlorine to aluminium and titanium to ethyl. So this is how you can see the structure of the catalyst will be, and during the reaction you can see, so this bond breaks here and this breaks here in this way, and you can see the structure of this uh, Ziegler-Natta catalyst. And when this happens, you can see that it is going to generate the active catalyst. Okay, so this is how, so you make this bond here with chlorine with aluminium, and from titanium to ethyl, and this breaks here, and one of the chlorine is removed, and this ethyl is going to attach with this titanium, and you can see you are going to generate with somewhat TiCl3 position will be there, and this ethyl group is been attached here, and there will be one vacant site created here. Okay, like this, and you can see the oxidation state of titanium will be +3 in this case, and now this becomes the active catalyst and ready for oxidative addition of it becomes unsaturated now, and that's why it becomes we can't say, but addition process is easy now. So ethylene, so here alkene can be easily accommodated here in this case. Okay, so this is how the mechanism of this catalyst we can show here. Okay, so this is what about the about the advantage, if you see, of this is it can be treated at a very optimum temperature, this catalyst, at 333 to around 343 Kelvin. And if we see the pressure also, so pressure also is a normal pressure, 6 to 7 atm. Okay, so this is what is very optimum temperature and pressure. This catalyst can be utilized. Okay, and you know that this and this is very beautifully, you can see the linear polymer is obtained from this Ziegler-Natta catalyst, which is not possible from free radical mechanism. Okay, so if you go for free radical mechanism, so you are ending with the very atactic type of polymer. Atactic means the functional groups are not attached. The functional groups are not attached exactly. You can say randomly they are attached, and that's why so such type of polymer tactic is going to be the product by free radical mechanism. But if you see this Ziegler-Natta catalyst, so you are going to see that the polymer obtained is having exactly the on the same position, the functional groups are attached, and this becomes very good polymer. Okay, good linear polymer with good functional properties. So this is what about the, you can say, the use of this catalyst here. Then the second point here, so you know that how is the polymerization taken place. So whenever you take any monomer, so this monomer is going to convert it into polymerization product. Okay, so and whatever this product we get, that is polyethylene, so this is usually we know that it is used in making the dustbins, buckets. Okay, and so many things, pipes nowadays, pipes is not bottles, etc. So like this this is the application of this polyethylene is used in synthesis, in manufacturing of all these items here. And whatever the polymers we are getting from this catalyst, they are of high density, very good quality. They are of high density, very good quality, or with a high melting point, and with superior quality, and with superior quality. Okay, so this is what we can see, that whatever we are going to get isotactic polymer from this Ziegler-Natta catalyst is having all the good qualities here, with compared to the other qualities, the negative of this reverse of these qualities in the presence of different without catalyst, that is a free radical mechanism. So this is what we can see as uh, and the second this we can go for now. If you see the mechanism of this, how it is going to obtain, how it is going to react with this. Okay, how the polymer is going to form here. So if you see the mechanism, now let me see. So if you see that, take this titanium here. Okay, and this is your, as I said here in the before, that there is the attachment of your CH2 CH3, that is your ET, and there is a vacant site here, and I will take here chlorine Cl. Okay, so there is a vacant site here. Now this, in this we have liberated here, and from when it goes out, so TiCl3 also you can show, and one vacant site is liberated, or is created here, and CH2 ethyl group is attached here, as I shown earlier case. Now this is the active site. Now this is the active part of the catalyst. Now what will happen, so there will be coordination of now CH2 double bond CH2. So it's not exactly the oxidative addition, so it's a coordination of this now CH2 group into this vacant site, and you are going to get here now CH2. Okay, from the pi bond, so I can take it in like this, CH2, CH2, and there is already here CH2, CH3, okay, and other Cl I can take it in this way, like this, okay. Now there is a coordination of in this way CH2. Now as we have learned from the catalysis coordination organometallic chemistry, that there will be transfer now, that is called the migration of the methyl group will be there. So what will happen, so there is going to form before going to migration, so that is going to form the four-centered transition state, okay, four-centered transition state. So where I will take it here in this way. So what will happen here, so like this, so here CH2, CH3, so here it is, I will take it as uh, like this, will take CH2, CH2. Now this is going to bind with this here, like this. So when this is having attachment with this carbon, so this double bond will have the partial now here, so it also will break, and this is going to happen. So here and here also it is going to happen like this. So like this, a four transition state is going to obtain here in this case, okay. So where the double bond vanishes and this titanium gets bonded in this and this carbon is bonded with this, like this, 1 2 and 3 and 4, 1 2 3 4, 1 2 3 4. So four center transition state is obtained here in this way, see here, like this, okay. So where double bond is collapsed here. Now next step is what, now this is going to transfer here, okay. So this bond is happening, and now you can see that this will break now, and here again this vacant site is created here, like this, okay, and this whole part is going to attach here. So I will write here again CH2, CH2, and here both CH2, CH3, like this ethyl group, okay. So this is attached here, and this as usual chlorine. So like this it goes for propagation, like this it go for propagation. This is your initiation step, and like this it goes on propagation in this way, okay. Now next what will happen, again this vacant site will be attached by the alkyl here, like this, okay. And ultimately I can show here it is going to form this way, titanium is there, again this is going to attach here, and this Cl is as usual, like this. And what will happen here, so I'm going to get now CH2, 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 CH2 n times I can take here with Et, like this, okay. So this is what I'm going to get here, like this it goes on like this, and again there will be the vacant site created here, and you can see this goes on, so that's why n times I have taken here. So that is what it goes, and that we call as propagation, we call it as a propagation. And finally you can see there is termination now, there is termination, where beta hydride elimination takes place, where beta hydride elimination will takes place here. So this I can this the same thing I can take it as a titanium is there, so I will take in this way CH2, CH1 of the hydrogen I will take it out, CH2, CH2 n times, and here Et is there, okay. Now other things is as usual, Cl, 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 and there is a vacant site created here, and ready for again. But before that, termination is taking place here. And how the termination takes place, by beta alpha, this is alpha and this is beta, so beta hydride elimination, so this hydrogen will now be attached here, okay. There is already vacant place here, vacancy is here, so this hydrogen from the beta carbon is going to be attached here, and this will be terminated, and you are going to get now here, so this compound you are going to get here CH2, so this hydrogen goes, so it becomes double bond here, so CH, CH2, CH2 n times, and this is your Et. So this is how polymer plus, now this is a remained here, so this hydride which is transferred here will attach to here, and other chlorine will be as usual, like this. So this is what I get my I get this the final product here, and after termination, you can see that I am going to this polymer or polymer polyethylene compound like this. Okay, so this is how I get the polyethylene from the with the help of this homogeneous catalyst, which is a Ziegler-Natta catalyst. Okay, so this is how this is how we can say that the initiation as well as the propagation, initiation and termination been is been followed here. Now if you see the some of the features of this, so we can see this is the first main features of this polymerization. So this will be is very much important and asked in all the semesters here as in the examination. So mechanism is very much important, so don't get confused with the mechanism. So everything I have explained here, so you also can practice this in the home. Now if you see, so here the main feature is this is carried out in a mild condition. Okay, so which required hazardous condition in other process. So this in this Ziegler-Natta we require mild condition, and this is stereochemical controlled. That means we are going to get isotactic type of very good polymer here. And if you see the next any desired polymer, we are going to get desired controlled polymer we are going to get here, and that is the linear to the level of 100% linearity we are going to get here. So in most of the you can see in industrial manufacturing, so isoprene, which is a natural rubber we call it, that is your CH2 double bond C CH double bond CH2 with CH3 here. So this is your natural rubber that is called isoprene. Okay, which is present here in the wood as a natural rubber. So this in the presence of now whatever we have learned Ziegler-Natta catalyst, taking this and this same mechanism goes on, and we are going to get the polymer here, that is your CH2. This will shift here, double bond C double bond, this is CH3 double bond CH2 n times like this. Okay, C double bond CH single bond CH2 n times. Okay, so this isoprene polyisoprene. So from isoprene I'm going to get polyisoprene with the help of Ziegler-Natta catalyst, and the speciality of this is we are going to get 100% linear polymer, 100% linear polymer. So this is nothing but your 1,3-butadiene 1,3-butadiene 1 2 3 yeah 1,3-butadiene. Okay, so 1,3-butadiene, so you are going to get this isoprene here, so polyisoprene here from this compound. So like this this is what I can say that that the different concepts of the polymerization, so I think we have learned here. Okay, so propagation, how it takes place, force centered, how there will be how the beta transition takes place, and this sometimes is also called as this cycle whatever we have learned, it is also called as Cauchy-Ullmann mechanism. Okay, Cauchy-Ullmann mechanism like this. Okay, so whatever this polyethylene we have here seen, so it is also called as Cauchy-Ullmann Ullmann mechanism. Okay, so sometimes if they use this word, we should know that this mechanism also called with this name. So like this I think I have completed, I have used all I think points here for the polymerization, and where the pi coordination takes place, and yes, definitely advantage also we have learned in this. Okay, and hope you understood this polymerization concept. So make a notes very full points on this as I said, and in I think as time is video time is more here, so in the next video we can learn regarding the isomerism concept by using this catalyst, homogeneous catalyst. Okay, so that we will learn in the next video. Thank you.